Hello, Math 6B peoples. I got a video for you today. This one is related to sort of the derivation of how Fourier coefficients work. This one's all about orthogonal functions, and it's sort of a generalization of some of the linear algebra concepts from Math 4a and some of the vector concepts, namely the dot product and orthogonality from Math 6a. Okay, so the idea is, so here's the background stuff, and we'll explain how to use this in a second. So basically, there's a definition here. If we got a vector space, so big V is the name of the vector space, n is however many dimensions it is. The n could be infinity, by the way, and in fact, the particular vector space we use for Fourier series is infinite dimensional. It's equipped with an inner product. Okay, so this is some extra structure for a vector space. This sort of allows us to define things like distance and direction and relative directions and things like that. And suppose we have a basis B for this vector space. So B is the set of vectors B1 hat, B2 hat, dot, 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 Bn hat. And I put little hats above them to denote that they're probably unit vectors. Okay, so if B is a basis for the vector space V, then B is a special kind of basis, an orthonormal basis for V if the following two things are true. So one, if all of the vectors in B are mutually orthogonal. So every vector in B is orthogonal to every other vector in V. And the way you test for orthogonality is dot two vectors, and if you get zero, they're orthogonal, right? If you don't get zero, they're not orthogonal. All right, so, and also if all the vectors in B are unit length. So if you take any one of those vectors in B, dot it with itself, if you get one, then it's unit length, right? Because the dot product gives you magnitude squared. The dot product of a vector with itself gives you magnitude squared. All right, so if this is a case, if B is one of these very special bases for a vector space that's orthonormal, then it becomes easy to express vectors in terms of the basis vectors. So namely, you can rewrite any vector in your vector space as just some constant times B1 plus some constant times B2 plus da 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 plus some constant times Bn. Now, if it wasn't an orthonormal basis, then this, we could still do this, but it would be harder to figure out the constant. So basically, to figure out the coefficients, A1, A2, so what numbers go in front of those things, then all we got to do is do the dot product of our vector with each of the basis vectors. Okay. Also, by the way, there's something called Parseval's identity. So if you have an orthonormal basis and you figure out all of those coefficients, the inner product of V with itself is just the sum of the squares of the coefficients. This is essentially a generalization of the Pythagorean theorem, and it's called Parseval's identity, named after a guy named Parseval. Okay, so I got some examples for you here. So one, I wanted to talk about some vectors in R3. Okay, so we'll start off with the standard basis, I, J, K. And we want to show that this is an orthonormal basis. So this should be a nice, easy exercise. It's, if you have a visual of I, J, and K, it's like, yeah, those are all unit vectors and they're all perpendicular to one another. So they should be orthonormal. So our inner product for R3 is just the regular old dot product. So let's see here. So let's show that the standard basis for R3 is in fact an orthonormal basis. So show that the set I, J, K is orthonormal. We know it's a basis for R3, so, right? Because it's literally the standard basis, right? Okay, so the way we do that is first one, we have to show that, well, what's I dot j? So we do the dot products of all the vectors with all the other vectors. So remember, I is the vector, 1, 0, 0, and then j is the vector 0, 1, 0. And if you work out this dot product, you get 0, you get 1 times 0, which is 0, plus 0 times 1, which is 0, plus 0 times 0, which is 0. Yay, you get 0, yay. And if I do I dot k, so if you remember, so I is 1, 0, 0. If you remember k was 0, 0, 1. And you could very quickly tell 0 plus 0 plus 0. Yeah, that's also 0. Cool. So I is perpendicular to k. So cool. And what else we got? J dot k. So J was 0, 1, 0, and K is 0, 0, 1. And you can very quickly verify that if I dot these two things, I also get 0. So these three dot products together show us that that I, J, and K they're all mutually orthogonal. Okay, so at least every vector in our set is orthogonal. All right, so now the next thing we have to show is that each one of them is a unit vector. So how do we do that? Well, if the dot product of a vector with itself is 1, then it's a unit vector. So what's I dot I? So I dot I, well, that's 1, 0, 0, dotted with 1, 0, 0, and then that's 1, yeah, right? 1 times 1 plus 0 times 0 plus 0 times 0. So that's 1. Cool. What's J dot J? Well, that is 0, 1, 0, dotted with 0, 1, 0. And that's also 1, right? Because it's 0 plus 1 plus 0. Okay, yeah. And then what's K dot K? You won't be shocked to find out that it is in fact also 1, 0, 0, 1, dotted with 0, 0, 1. That is 0 plus 0 plus 1. That's 1. All right, cool. So this bit right here shows that I, J, and K are all unit vectors. They're normalized. So now we have shown that the standard basis for R3, IJK, is in fact orthonormal. Okay, so what was the second part of this doodad? So now that we've shown it's orthonormal, we have this vector here, 2, comma, negative 5, comma, 6. We want to show that we could rewrite this vector as v dot I times I plus v dot j times j plus v dot k times k. And, you know, this just gives us an alternate way of writing it, right? So the v, what was that? It was 2, negative 5, 6. Well, let's see here. Well, what's v dot I? So v dot I would be 2, negative 5, 6, dotted with 1, 0, 0. Okay, so that's 2, right? 2 times 1 plus 0 plus 0. All right, so that's 2. All right, and then what's v dot j? Not surprisingly, v dot I just gives you the x component of the vector. V dot j would be 2, negative 5, 6, dotted with 0, 1, 0. And so that would be 0 plus negative 5 times 1 plus 0, so that's negative 5. And not surprisingly, the dot product of v and j gives you the y component of the vector. And then v dot k is our vector 2, negative 5, 6, dotted with 0, 0, 1. And then that would be 0 plus 0 plus 6 times 1, so 6. And then that, not surprisingly, gets us the z component of the vector. And so according to our theorem then, the v should be the same thing as v dot I times I plus v dot j times j plus v dot k times k. And then since we did all of these dot products, we get our v is in fact 2 times I plus negative 5, so minus 5, I guess. So minus, whoa, wrong pen. Minus 5 times j, and then plus 6 times k. And yay, all right, and that you know, if you're familiar with this stuff from Math 6a, then yeah, like that's just an alternate way of writing this vector. Okay, so this was like a trivial version of this, but it's just to show you that this dot product stuff really works. And we could use a different basis for R3, in fact, so if we look at our second basis here, so all right, so we got this other set of vectors in R3, which I also claim is an orthonormal basis for R3. So let's see here. Well, so let's see here. So what was this set of vectors? So we got this other set. So 1 over root 3, 1 over root 3, 1 over root 3. That was one of the vectors. The second vector in our set was 1 over root 2, 0, minus 1 over root 2. So 1 over root 2, 0, minus 1 over root 2. And then our third vector is, what's our third vector? 1 over root 6 minus 2 over root 6, 1 over root 6. Okay. So that would be 1 over root 6, comma, minus 2 over root 6, comma, 1 over root 6. All right, so for this one, I'm going to skip the part of showing that it's orthonormal. You should check. So if I call this one like say B1 hat, if I call this one say like B2 hat, if I call this one say B3 hat, so if you check for, so this is orthonormal if this set is orthonormal if, so the dot product of any two different vectors is 0, so B1 dot B2 is 0, B1 dot B3 is 0, and B2 dot B3 is 0. And so, and then also if any vector dotted with itself is 1, so B1 dot B1 is 1, B2 dot B2 is 1, and B3 dot B3 with the little hats there is 1. And so feel free to verify that this is in fact true. Okay, so now this being the case, we should be able to take our same vector and write it as a linear combination of these 3 vectors. So we should be able to rewrite the vector v equals 2, negative 5, 6 as v equals some constant times b1 hat plus some other constant times b2 hat plus some other constant times b3 hat. And the way we figure out these constants is so where a1 would be the dot product of v with b1 hat, and a2 would be the dot product of v, I guess that's not v1, it's just v, with b2 hat, and a3 should be the dot product of v with b3 hat. So notice I'm writing, instead of writing it as a dot product, I'm writing it as this more general inner product. So we're going to move to this notation basically when we're dealing with the quote unquote inner product, or the equivalent of a dot product for functions. Okay, so let's see how this works. All right, well, what's A1? So A1 is V dot B1, right? So A1, that coefficient would be the dot product of 2, negative 5, 6 with our B1. What was our B1? 1 over root 3, 1 over root 3, 1 over root 3. Okay, so dotted with 1 over root 3, 1 over root 3, 1 over root 3. And we evaluate this dot product, we get 2 over root 3 minus 5 over root 3, and then plus 6 over root 3. And we clean it up a little bit. That's 2 minus 5 plus 6 is 3, so that's 3 over root 3. And, you know, can't help myself. Rationalize it, root 3 over root 3, so that's 3 root 3 over 3. That's root 3. Okay, so the A1 is square root of 3. Okay. So then what's the A2? So the A2 would be the dot product of our vector with the second basis vector, so with B2. So it was B2, 1, 0, minus 1 over root 2. So dotted with 1 over root 2, 0, minus 1 over root 2. If we work this out, so this is 2 over root 2 plus 0, and then minus 6 over root 2. Clean that up a little bit. That's minus 4 over root 2. And then if I, rationalize root 2 over root 2, then I get A2 is, what does that end up being? Minus 4 times root 2 divided by 2, so minus 2 root 2. Okay, so there's our A2 and A3. So that would be the dot product of our vector 2 minus 5, 6 with our third basis vector. So that would be 1 over root 6 minus 2 over root 6, 1 over root 6. So come on now. All right, so 1 over root 6 minus 2 over root 6, 1 over root 6. All right, and so that would be 2 over root 6 plus negative 5 times negative 3, so plus 10 over root 6. And then plus 6 over root 6. All right, so this would be 12, 18 over root 6, which if I rationalize, root 6 over root 6, this is 18 times square root of 6 over 6, so 3 over 3 times root 6. So our A3 is 3 times root 6. Cool. Right on. So what now? So let's see here. So now we should be able, now that we've got our A1s, we should be able to write this as A1 times B1 hat plus A2 times B2 hat plus A3 times B3 hat. So let's see. So we should get, if this works at all, that our V are 2, negative 5, 6. That should be equal to our A1, which was square root of 3, times our first basis vector, which was 1 over root 3, 1 over root 3, 1 over root 3. And then plus A2, so minus 2 root 2, times our second basis vector, which was 1 over root 2, 0, minus 1 over root 2. And then plus A3, so plus 3 root 6, times our third basis vector, which was that thing, 1 over root 6, comma, negative 2 over root 6, comma, 1 over root 6. All right, now keep in mind, the whole reason this is useful is that you can only do this if the basis is orthonormal. So let's check. This should be the case, right? Like the 2, negative 5, 6 should be this, like the sum of these three things, right? So let's just check. So, well, if we distribute the root 3 here, that's just cancels all the root 3's on the bottom, so that's 1, 1, 1. If I distribute the minus 2 root 2 here, the root 2's cancel, and then I get plus, so that would be negative 2, comma 0, comma positive 2. And then if I distribute the 3 root 6 here, that'll cancel out with the root 6's on the bottom, and then the 3's, the 3 gets multiplied in through the top. So that'd be 3, comma negative 6, comma 3. And if we add all of these vectors up, so the first, the x component, 1, minus 2, which is negative 1, plus 3, that's 2. And then if I do the y components, 1 plus 0 minus 6, that's minus 5. And then if I do the z components, 1 plus 2, that's 3, plus another 3, that's 6. Oh, yay, cool. So check, this actually works. Right, so it's relatively easy, like the alternate thing would be like solve a 3x3 matrix equation to figure out these coefficients, to take an orthonormal basis and figure out how much this vector points in each of the, and get figure out any vector as a linear combination of these. Just got to do a bunch of dot products, and dot products are relatively easy things to do. Even if their dot product is like an integral, right? Usually, well, all right, well, I guess this is a relative term. Some of these integrals can end up being pretty hard. So here, now I've got a new space, new inner product. All right, so the vector space is polynomials of degree 2 or less. This is known as, of course, P2. And the inner product here is defined as, so now I'd be doing the inner product of two functions. So I multiply the two functions and integrate them from 0 to 1. Note, for two particular functions, the result of this is a number. So this is like a way to multiply functions together in order to get a number. All right, so here I claim that these three basis functions form an orthonormal basis. I'll let you verify this. So let me copy these guys down here. All right, there they are. So, all right, so now you can verify that. Okay, so since the inner product here is just, so the set P1, P2, P3 is orthonormal if, so the inner product of P1 of X and P2 of X is 0, and the inner product of P1 of X and P3 of X is 0, and the inner product of P2 and P3 is 0. I think for a lot of your homework problems, you don't have to check the unit length thing. And then also, so that's the ortho part of the orthonormal, right? Like they're all mutually perpendicular to one another. And so, by the way you'd convert the way you'd actually do these is like, for this one, it'd be 0 to 1, P1 of X times P2 of X dx. So you'd multiply them, do the integral, and you should get 0. All right, and then the same thing's true for the other two. And then also P1 with P1, that should give you 1. P2 with P2, that should give you 1. And then P3 with P3, that should also give you 1. So these conditions are why you end up with these like square roots and stuff there that probably, if you just insisted on it being orthogonal, you can still recover a lot of these properties. But okay, so now what I really wanted to do, and you could check that those things are all true, is take this function, 2 times quantity x minus 1 squared, and I wanted to rewrite it in terms of these basis polynomials. So, okay, so let's see here. So we want to take f of x equals 2 times x minus 1 squared, which, by the way, I might as well just, squared. So it's 2 times x squared minus 2x plus 1, or distribute the two, for the sake of actually doing the integrals, I probably want it multiplied out. Okay, so I want to use this version of f of x. Now I claim that this f of x should be the same thing as some constant times p1 of x plus some other constant times p2 of x plus some other constant times p3 of x, where a1 is the inner product of f of x with p1 of x, and a2 would be the inner product of f of x with p2 of x, and a3 would be the inner product of f of x with p3 of x. Well, let's just do these inner products, see what we get. All right, so a1. So that would be the inner product of f of x with p1. So that would be the integral from 0 to 1 of, so our f of x, which was in written out form 2x squared minus 4x plus 2. And then times p1, which was just 1 dx. All right, now polynomials from 0 to 1 are pretty great, because like 2 times 1 cubed over 3, so 2/3. Minus 4 times 1 squared over 2, so minus 2. And then plus 2 times 1, so that's plus 2. All right, and so we get A1 is 2/3. Oh, okay, that one's not too bad. For the others, we're going to have to spend some time multiplying stuff out. All right, so A2 should then be, with this dot product, the integral of our function, 2x squared minus 4x plus 2 times root 3 times 1 minus 2x, because that was our P2 of x. Okay, this one's going to require a little bit more computation, right? Because, by the way, that was our P2, yeah? Root 3 times 1 minus 2x, yes. Okay, because we got to like multiply everything out before we integrate. So that's fine. I'll do that real quick. Woo! All right, so I did that real quick, and so our integral simplifies down to this when we multiply everything out, just keeping the root 3 factored out there. And so let's evaluate this integral. So we'll get a root 3 times, so minus 4 times 1 to the 4th over 4, so minus 1. And then plus 10 times 1 cubed over 3, so 10 over 3. And then minus 8 times a half, so 4. And then plus 2 times 1, so 2. And then we clean this up a little bit. And this whole thing simplifies down to A2 is root 3 over 3. Whew. All right. So almost there. Now we've got A1 is 2/3. We've got A2 is root 3 over 3. Now let's see what A3 is. So A3, according to this thing, should be, well, I got to go way back up. It's the integral from 0 to 1, because that's how our inner product is defined here, of our function, 2x squared minus 4x plus 2. So the integral from 0 to 1 of 2x squared minus 4x plus 2, and then times our third basis function, which was root 5 times 1 minus 6x plus 6x squared. Okay, so times root 5 times 1 minus 6x plus 6x squared dx. All right, and all right, let me rush through this integral real quick because I feel confident everybody can do it. And whoa, all right, that was a lot of like the algebraic simplifications right there. And I actually went through this real fast. I didn't even show all my work, but hopefully you can follow. So the A3 ends up being square root of 5 over 15 after all of these computations. Okay, so what did we just do again? Well, we just showed that the polynomial 2 times what was our original polynomial? I'll write it in the original form there. 2 times x minus 1 squared. That should be the same thing as our A1 2/3 times our first basis vector 1 plus our A2, which was root 3 over 3, times our second basis vector. And what was our second basis vector? It was way the heck up here. It was root 3 times 1 minus 2x. Okay, so times root 3 times 1 minus 2x, and then plus our A3, well, that's very conveniently right there, root 5 over 5 times our third basis vector, which I believe also had a root 5 in it. Where was that at? It was root 5 times 1 minus 6x plus 6x squared. There it is. So times root 5 times 1 minus 6x plus 6x squared. And we have effectively rewritten this original polynomial as a linear combination of these other polynomials. Okay, and so provided that you have an orthonormal basis, you can always do this using the dot products as opposed to the regular linear algebra methods that you might use. And this is especially useful when you extend this to infinite dimensional spaces when you don't really have a matrix to set up if you needed to. All right, so I hope you guys get the hang of this orthonormal basis stuff and with this inner product stuff. We won't be doing a whole lot of it there. It's mostly there to justify why the formulas for Fourier series work. But you do have some problems on it that you got to do, so enjoy.